For the second part of Lecture 8, we're introducing the all-important idea of functions. And it's really important that you understand the terminology here and how it works. And so we're going to take our time going through some examples. And please, you take time to make sure you understand how this lecture works. Okay, first of all, we're going to make some definitions. A relation is just a correspondence between two sets. Okay, it's some way of relating the elements in one set to the elements in a second. And it's expressed as a set of ordered pairs where x comes from the first set and y comes from the second set. The domain is the set of all first elements. The range is the set of the second elements. Okay, now this is kind of abstract, so we're going to look at some examples, but just think of it as being a set of ordered pairs. The domain is the set of all x values, and the range is the set of all y values. Now we don't specifically say x and y values because, as in a previous example, our variables may not always be x and y. We saw that in the last example of lines that we just worked. Okay. A function is a specific type of relationship, and it says that if I start out with an element x in set A, there is exactly one y that corresponds to that x value. Okay, so given an x, exactly one y. So let's look at a couple of examples. Let's look at these relations. They're both relations because they're both sets of ordered pairs. The domain is the set of x values. So for our first set, the domain is the set of x values, -1, 2, 0. Now I don't need to rewrite 2. Okay, it's the same number, so the domain is 3 numbers, -1, 2, and 0 in that set. The range is the set of y values. Okay, so I have 0, 4. I don't need to repeat 0, but I also have -2. Okay? Now, let's think of this kind of schematically. Let's put these in sets. So set x, the domain is -1, 2, and 0. And the set y has the point 0, 4, and -2. And our relation corresponds those, which we see by looking at the ordered pairs. So we know that number 1 is associated with the y value of 0 under this relation. 2 is associated with the y value of 4. Okay? 0 is associated with the y value of 0. And so far, every element x has been associated to exactly one value y. But look at the last ordered pair. That same x value of 2 also is assigned to -2 by our relation. Okay, that's a problem in terms of being a function, because a function says that if I choose an x, it's going to match to exactly one y. So this is not a function. Okay, does that make sense? Because here's an x, and there are 2 different y values that correspond to it. Okay, let's look at this next example. Again, we start with the domain, which is a set of x values. We have -2, -1, 0, 1, and 2. 5 different x values. Okay, the range y is, let's see, 0 and 2 and 0 is a duplicate, and 2 is a duplicate, and 0 is a duplicate. So we only have 2 elements in the set Y, in the range. Okay, now let's see what's happening here. So here's our set of X values. And they are going to match under this relation to just 2 different Y values. Okay, so let's look at what it does. The ordered pairs tell me, oh, -2 goes to 0, -1 goes to 2, 0 goes to 0, 1 goes to 2, and 2 goes back to 0. Now the question is this a function? And what do we think? Well, notice that each X is assigned to exactly one Y. There is no X that is associated with there's not one X value that's associated with 2 different Y values. So this is a function. Now, does it matter that we have several X values? For example, -2, 0, and 2 all correspond to the same Y value, and the answer is no. The key is that each X value has a unique Y value associated to it, and the answer is yes. And there's another way that we can look at the difference in these 2 relations. They're both sets of ordered pairs. Notice that in this set of ordered pairs, we had 2 ordered pairs with the same X value. As soon as that happens, we're going to have this scenario where you have one X value associated to 2 different Y values. And so a relation will be a function if no 2 ordered pairs in the relation have the same first or have the same X value. That's how you can tell, okay? In this second example, notice that we do not duplicate any of the X values. So that is a function, okay? All right, now that's one way, but we usually don't think of functions in terms of just strictly sets of ordered pairs like this. More often, we're going to be looking at algebraic equations and using those and trying to determine if or whether or not it's a function, okay? And we know that we have a function, and here's the key. For each value of X, there is exactly one Y. That's the key. That only one is the key part of the definition. Okay, so how do we figure out if Y is a function of X? We solve for Y and then see what happens in terms of the X values. Okay, so if I solve for Y, I get that Y equals 4 plus 3x minus x squared. Okay? Now, let's choose an x. Say, let's choose an easy one, x equals 1. That means that y is 4 plus 3 times 1 minus 1 squared, which is 4 plus 3 minus 1, which is equal to 6. Is there any ambiguity? Could I come up with another y value associated to 1? And the answer is no. And I think you can see that's true no matter what x value I choose. So this is a function. Because given an x, there is exactly 1y. That's associated to it. Okay? All right. Now let's look at a second example, and we'll do the same thing, solve for y. And we get that y squared equals, let's see, 4, and bring this over, and I get what, 4 plus 2x? Y squared equals 4, subtract x from both sides. Okay? And then I have to take the square root of both sides to solve. And remember, when I take the square root, because it's an equation, y squared equals this quantity, I have two options, plus or minus the square root. So I think you can see where this is going. Let's let x be the specific value of 0. Then y equals plus or minus square root of 4 plus 2 times 0 according to our function, or according to our equation, okay, which is plus or minus the square root of 4. And we know that that is plus or minus 2. So look what happens. If x equals 0, y equals 2 or negative 2. That violates the very idea of function, because there's an x that has two specific different y values. Okay? So it's not a function. So a function says, given an x, there is exactly one y. And because that's the case, we can define function notation. We can define y equals f of x to be the unique function value associated to x by f. Okay? And it's because it's a function, we know there's going to be just one specific y value. Now we're going to introduce a new terminology here. The argument is what's inside of the parentheses here, what you're taking f of. Okay? So this is the argument. Okay, and that is what we call the argument of the function. And once we choose the argument, we evaluate the function by replacing every x by that specific argument. Okay? Now, let's do it. It's easier to see it with examples rather than words, so let's do that. Okay. F of x equals 3 minus 2x. Let's find f of negative 2. Now the argument is negative 2. And what does my function tell me to do? Replace every x with the argument negative 2. Okay, I replaced x with the argument. Okay, and so actually I should put this over here. This negative 2 goes where x was in the function. And so that's 3 plus 4 is equal to 7. Okay, now notice 2 and 3. In 2, the argument is a. So f of a minus 1 says, take our original function with argument a. So I replace x in my function with the argument. And then I have a minus 1 off to the side. Okay, so f of x is 3 minus 2x, so f of a is 3 minus 2a. And then I subtract 1. And what do I get? 3 minus 2a minus 1 equals 2 minus 2a. Okay? Now, let's compare that to f of the quantity a minus 1. So this is our argument. This is representing x in our function. So if we write this down, f of x equals 3 minus 2x, I am replacing x with the argument a minus 1. So it's going to be 3 minus 2 times a minus 1, because I am replacing x with a minus 1 in the original function. Does that make sense? This is the key. You really have to understand this. This is our argument. And so wherever I see x, I'm going to replace it with the argument. Okay? And so I get 3 minus 2a, and remember I'm going to distribute, plus 2, so that is 5 minus 2a. Okay? Another way to see all of this is to think of this. So f of x is 3 minus 2x. Okay? Think of replacing x with a blank. That blank is your argument. So f of a is just 3 minus 2, filling in that blank with a. F of the quantity a minus 1 replaces that blank with a minus 1. It fills it in with the argument. So maybe that helps. F of x is 3 minus 2x. F of blank is 3 minus 2 times the blank. F of a is 3 minus 2a. F of a minus 1 is 3 minus 2 times a minus 1. Okay? And what we observe big time is that f of a minus 1 is not the same as taking the function and evaluating it at a minus 1. We have two different arguments. All right? Okay, let's look at this example. We're going to find and simplify the difference quotient, which is given here, for a specific function f of x. Okay, this is a calculus quantity. That's why you see it in all of these pre-calculus texts, because you're going to need to work with this when you move on to your calculus course. So let's kind of go back to this scenario that we had up here. Let's see if we can figure things out. So here's our function. F of x equals x squared minus 2x. Or another way to say that is that f of whatever our argument is takes that quantity squared and subtracts 2 times that quantity. Okay, does that make sense? So our difference quotient asks us to find f of x plus h. Let me do it with a different color. Maybe that will help. And according to our function, wherever I see the x, think of that as a blank, I'm going to replace it with x plus h. Okay, it's a replacement. Wherever I see an x in the original function, I replace it with x plus h in my new function with the argument x plus h. Okay, and it corresponds wherever there was an x in the original function. Okay, so, and please take a little while to make sure you understand why that's working, but we're going to go ahead and with that we're going to find our difference quotient. Okay, now f of x plus h, remember, is just this quantity right here. It's x plus h squared minus 2 times x plus h. That was f of x plus h, okay? That's where that comes from. f of x, well, that's just our original function. Be sure to have parentheses. I'm subtracting that entire quantity. So f of x plus h is right here. F of x is here. And we are dividing the whole thing by h. Okay? Again, we replaced x with x plus h in my function originally, and then we subtract f of x. Okay, now the rest is just algebra. Okay, remember that we square a quantity, we're going to have a middle term using our special product. Okay, and I can distribute minus 2h, and here I can distribute that minus x squared plus 2x. Remember, we're trying to simplify this expression. Okay, and what do I get? I can drop the brackets now. It's x squared plus 2xh, and I can drop the parentheses, minus 2x minus 2h minus x squared plus 2x, all over h. Okay, now what do we get? This is the fun part. We observe that we have some cancellations. The x squareds cancel. Okay? The 2x's cancel. And what are we left with? We're left with 3 terms. And notice that there's an h in each term. Okay, that's not an accident. That's a function of the way that this is set up originally. And so when you're doing these examples, you expect that to happen, because what that allows us to do is to factor an h out of the numerator and cancel with the denominator, and we get 2x plus h minus 2. And there we go. This is a really good example. Make sure that you follow how it's working.